All right, so we're going to start with number 3 here with our flight attendant rolling the suitcase. And how much, at what angle does she roll the suitcase? I think some of the key things to understand here and to express your understanding in your why are that for there to be work done, John, don't forget the hat, please. For there to be work done, the force and the distance must be in the same direction. So while she pulls upwards on the handle here, upwards and sideways, with 25 newtons, not all of that force creates work. Only the part of the force that's parallel to that horizontal distance that she's moving creates work. So it's key to be able to show that in this Y here, in your Y. So for number 3, you might say only force in the direction of motion creates work. That's kind of the key here. So not all of, you could say it other ways, not all of the force she applies creates work. You could say only a component of her force creates work or goes into work. You could also look at it the other way, and only if we were to look at the distance, we could say, well, we need to figure out how much of this horizontal distance is in the direction of the force she applies, and that we can figure out the work that way. I think we're going to be better using our equations here. And one thing to realize here is that the angle we have, we're given, or we're asked to find theta, is the angle between the force and the displacement, or the force and the direction of the distance. And that, if we're given that angle, we remember from our equation sheet that our W equals F delta D cosine theta, that theta is always has to be between the force and the direction of the distance. So really, for this one, we can start off with that equation, that the amount of work is the force delta D cosine theta. And now we look for things that we know. And we know the force that she uses. We know the amount of work that she does. And we know the distance. So really now it's just plugging it in. The amount of work, I'm told, is, for me, 1,010 joules. The force is 25 newtons. My distance was 58 meters, I believe. And, hold on just one second. And cosine theta, my only variable is theta, which I can solve for. Well, see, what I did is I looked at mine, and mine was in scientific notation. And so I converted it to regular notation to make it easier on some people to recognize as a number. Okay? So that's where I had times 10 to the third. What did you have times 10 to the what? So you had thousands also. Yeah. Did you move it over 3 places to the right? And now I have all my numbers except for my theta, so I solve for theta. If you need help individually on that one, let me know. I'll come and help you individually. All right, folks. I'm going to do number 6 here. All right. So remember, if you're working on a different problem, that's fine. Just try to keep the volume down a little bit so I can hear myself. Thanks, sir. All right. So number 6. In number 6, we have the swimmer doing work by pushing against the water Now, in this one, notice how they have the average horizontal backwards force. Because, again, that direction that we're looking at is horizontal, we can only consider the parts of the force that are actually horizontal. The swimmer is going to push down and back and up and back the whole time, but we're only taking the horizontal component of that. So that would be a good thing to note. Right off the top, in number 6, is that the work is done by the horizontal force acting through the horizontal distance. And then, of course, the other part that would be important to have in here is that power is the rate work is done. And it's really important that you understand that power is a rate, not I've heard a lot of people express it as the amount of work that gets done in a certain time. No, that'd be the amount of work you did. Or how much time it takes you to do a certain amount of work. No, that'd be the amount of time. It's got to be the combination, the rate that the work gets done, or is done. So here, let's see. Equations we'll need to make sure we have an equation for work. These are parallel, so we'll use our simplest one. And then the power we'll need the power equation. So the equations I would need to look up on my equation sheet is the one for work. That work equals force parallel and the magnitude of the displacement parallel. And mine for power, which says delta work over time. So those would be my 2 equations for part A now. The work he does is the force, in my case, was 90 newtons. 90.0 newtons through a horizontal distance of 1.8 meters. Which, in my case, should be almost 162 joules, I think. 162 joules. And then moving on to B, the power is the amount of work per time. And they're asking me to make sure that I do that in units of watts. So I know a watt is a joule per second. And if he does 130 strokes in a minute, then, what's that, 130? 130. So the amount of work that my swimmer does is 130 strokes. Each stroke he does 162 joules worth of work. And he does that per minute, which would be in 60 seconds. And I have all numbers again. And I'll end up with watts because I have joules per second. So if you need help individually on that problem, let me know, and I'll come around and help you look at the work you've done.